Okay, so today we're going to talk about the parabola, some of the key features of it, and then also how to graph it. So we're going to start with some of the important pieces of parabola. First thing we're going to talk about are the roots. These are the x-intercepts, so the places where it crosses over the x-axis. In this particular parabola, I can see them here and here. Okay. So fortunately, because we have a graph in this case, I can actually just read them off, and I can say my roots are 1 and 3. Just those x-intercepts. Okay. If we weren't so fortunate as to have a picture, we can also find the roots. Because they're on the x-axis, they occur when y is equal to 0, which, by the way, is why they're also sometimes called zeros of the function. Okay. Next key piece we want to talk about is the axis of symmetry. We're going to skip down a little bit. The axis of symmetry is that vertical line that happens to go through the vertex. You can see it here. And it's symmetry. It creates symmetry, so it basically acts like a mirror on my function. Anytime I have a point on one side, it's going to have an equidistant point on the other side. So again, this axis of symmetry acts like a mirror. For our purposes, these are always going to be vertical lines, so they're always going to look like x equals some number. And again, because we have this graph here, I can just say, okay, well, this is x equals 2. That's where we cross through here at 2. So my axis of symmetry is at x equals 2. And again, if we don't have a picture, we can still find them. The axis of symmetry has an equation that we can use, x equals negative b over 2a. So if we have the equation of the parabola, I can use a, and I can use b, and I can find the equation of the axis of symmetry that way. Now, next key piece is the vertex. The vertex is sometimes called the turning point, or the maximum or minimum point of the parabola. So this is always going to be here, okay, where it turns back around again. Okay. So again, in this particular parabola, I've got my vertex is the point 2, negative 1 looks like in this picture. Okay. And again, if we didn't have the picture, I can find it because I know it's always going to be on the axis of symmetry. So once I've found the axis of symmetry, I can use that plus the equation to find the vertex. Now I'm going to skip back a little bit because now that we've talked about the vertex, we can talk about maximum and minimum. So I know that a vertex is going to have a minimum if the parabola happens to open upwards, like ours does here on the right, and a maximum value, a high point, if it's got if it opens downwards, because we're going to have maximum there. The last piece I want to talk about is the y-intercept. We've already talked about the x-intercepts. The y-intercept, of course, is where the parabola crosses the y-axis. So in this case, up here at positive 3 is going to be my y-intercept. So y-intercept is 3. And again, if I don't have a picture, I can still find them because this is where x is equal to 0. So we've got roots of 1 and 3, axis of symmetry at x equals 2, a vertex at 2, negative 1, which by the way is also a minimum value for us here, and a y-intercept at 3. Okay, so now that I've looked at parabolas, I can talk about how to graph one if all we have is an equation. Okay. Now generally where we want to start is by finding the roots. This is a good place to begin, and we said that I can do by setting y equal to 0. So if I set y equal to 0 here, I'm going to have 0 equals negative x squared plus 8x minus 15. Okay. And I'll solve that equation. Now I'm not a big fan of how the x squared is negative, so let's divide both sides of the equation by a negative 1 to change that. So we'll still have 0 on the left, and then positive x squared, don't really need to write positive though, minus 8x plus 15. Okay. Now that's a trinomial, and I can factor it. Leading coefficient is 1, so I can just use the double bubble method. Okay. I've got x squared in the first term, so these are both going to be x's, and I'm looking for two numbers that multiply to positive 15 and add to negative 8. So that's going to be negative 5 and negative 3. Now that we've got it factored, I can set each factor equal to 0, and then solve these little mini equations. So here x is equal to 5, and on the right x is equal to 3. So I've got two roots, and I can graph them, okay, because these are my x-intercepts. So at 3 and 5 on the x-axis, I know that's where my parabola is going to live. Now that I've got two points on the parabola, I can also talk about my axis of symmetry because I know that that's symmetrical. It's always going to be a vertical line halfway between any 2 points. Okay, so now that I've got the roots, I can find a vertical line that's halfway between them. And that's here at x equals 4, so this is nice and easy. Now that I've got that, x equals 4, I can go ahead and find the vertex because I know the vertex lives somewhere on this axis of symmetry, so I know the x value must be 4. So I can actually plug 4 in for x in my equation, and that'll get me the y value for the vertex. So if we do this, we've got then y equals negative x squared plus 8 times x minus 15, and we'll simplify. So y is equal to 4 squared is 16, so negative 16, plus 8 times 4 is 32, minus 15, and if we add all of this up, we're going to get positive 1. So this is the y value. The x value, remember, is still 4, so my vertex is the point 4, 1, and I can graph this on my graph as well. Now 3 points really is enough to draw in a parabola, assuming you know the shape of it. Okay, so it doesn't come out as a straight line, it's kind of curvy. Okay, but it does open kind of outward and down. Okay. Now, we also have the option, if you are fortunate enough to have a calculator, to find a table of values as well. So if you want to talk about that, you can come and talk to me tomorrow, and we can go over how to get a table of values in the calculator. But fortunately for us, we have that option available to us, and so you could actually have gotten a couple more points on your parabola as well if you had the table of values to work from. Okay. Now, lastly, word problems. Okay. Now, the equation describes the height in feet of a ball thrown straight up in the air as a function of time. So I'm noticing that this equation has a t squared in it, which does mean it's going to be a parabola. Okay. So I can just kind of imagine this ball being thrown up in the air and eventually it's going to come back down again. This is basically what's going on here. So we said h is the height in feet. Height. Okay, and then t is going to be the time in seconds. Okay, and I'm asking about two different things. The first says, at what time does the ball reach its maximum height? So I want to know how long in time do I have to go until we get to that maximum height. Okay, this is that first question. So what you should be noticing, okay, is that this is going right through my axis of symmetry here, of course. Okay, so if I want to find the time to max height, okay, I can find the axis of symmetry. Okay. Now, if you remember from before, we said the axis of symmetry does actually have an equation, which is x equals negative b over 2a. So if I can get a and b from my equation, then I can plug in and I can find that axis of symmetry. Now, my equation up here is not actually in standard form yet, and to get a and b, I need it in standard form. So that means that I have to be in descending exponent order. That 16t squared has to come first, and then the plus 40t. So now I'm in standard form. I can see a is negative 16 and b is 40. So we can plug those into my equation for the axis of symmetry. So this is going to be negative 40 over 2 times negative 16. So negative 40 over negative 32, which is going to reduce to 1.25 seconds. And that actually answers my question, because it asked how much time until it reaches its max. So this is the answer, 1.25 seconds until it reaches its max. If I had asked how high does it get, I could have found that out. I could have plugged in that 1.25 seconds into my equation to get a height, okay? But we didn't ask that for you, so we'll skip that. The other question says, after how many seconds does the ball hit the ground? So if I want to know the time to the ground, okay. Well, when it hits the ground, we're all the way back here at the end, and this, of course, is going to be the root of the equation. Okay, so we found the roots before by setting y, or in this case h, equal to 0, which should make sense. On the ground, my height is 0. So if I set h equal to 0, I'm going to have 0 equals 40t minus 16t squared, and I can factor this. I can factor out a GCF here, actually, so let's do that. I can take out, it seems, a 4t. So if I take out 4t, then we'll have left 10 minus 4t. And we set these two factors equal to 0. So if 4t is equal to 0, then t is equal to 0 if we divide by 4. See? Okay, t is equal to 0. And if 10 minus 4t is equal to 0, well then 10 is equal to 4t. And so if I divide by 4, I'm going to get 2.5 is equal to t. Now you may be wondering why we have two possible values for t here, and that's because I have two roots. I have one at the beginning and one at the end. The one I want is when it hits the ground at the end, so what we want is 2.5 seconds. And there you have it.